Week 7, Cluster Evaluation Metrics and Interpretation. Clustering helps us discover groups within data. But how do we know if our groups are meaningful? This lesson will show you basic ways to measure and understand clustering results, step by step. Running the cell now. After watching, try the hands-on challenges at the end or share your questions in the comments. We need to suppress all warnings so our notebook output stays clear. Import NumPy as NP. We set the random seed to 42 for reproducibility. This keeps our focus on learning, not on warning messages. Running the cell now. Here, we set a random seed to ensure our clustering results are reproducible, and we suppress warnings to keep our output clean and focused. Although there's no visible output, this setup is crucial as it lays the foundation for consistent and clear evaluation of clustering metrics in the next steps. Notice how these preparations help us maintain stable and interpretable results throughout the lesson. Now, we will prepare our dataset for clustering. We are using the Mall Customers dataset. We import pandas. We load the data from an online source. We print its size and preview the first rows. This helps us see what we will work with. Running the cell now. Here, we load and inspect the Mall Customers dataset, which has 200 rows and 5 columns including key features like age, annual income, and spending score. Notice the mix of numeric and categorical data, which will help us identify meaningful clusters in later steps. This initial overview sets the stage for evaluating how well our clustering captures distinct customer groups. Look at the columns. What do you notice about the types of data? About the data. Each row represents a customer and basic information like age, gender, income, and spending score. We want to find groups of similar customers using clustering. Running the cell now. Next, let us prepare the data for clustering. We use only numbers, like age, income, and spending score. Clustering works best with numbers. This step keeps our results simple and clear. Running the cell now. Here, we've extracted the key numerical features, age, annual income, and spending score, that will be used for clustering. Notice the varied values across these columns, which will help the algorithm identify distinct customer groups based on their behaviors and demographics. This step ensures we focus only on relevant data for meaningful clustering results. Let us clean and scale our data next. We make everything on the same scale so each feature counts equally. This is like putting all numbers onto the same measuring stick. We use standard scaler to do this. Scaling helps clusters form properly. Running the cell now. Here, the code standardizes the features, age, income, and spending score, so they all have a mean of 0 and a standard deviation of 1. This step is crucial because it ensures that no feature dominates the clustering due to differences in scale. Although there is no visible output, this transformation prepares the data for effective grouping in the next steps. Ready to create our first clusters. What is clustering? Clustering tries to group data points so those in the same group are similar. People use clustering in marketing, biology, and more. Running the cell now. Let us see clustering in action with k-means. K-means is a popular clustering algorithm. We choose to create 3 clusters here. The computer will assign each person to one of 3 groups. Random_state keeps the results the same each run. Running the cell now. The code fits a k-means clustering model to the scaled data, dividing it into 3 groups based on similarity. Although there's no textual output here, the key result is the labels array, which assigns each data point to one of the 3 clusters. This prepares us to analyze how the data naturally groups, illustrating the core idea of clustering in this lesson. Now, let us check out our clusters visually. We plot clusters to see if our groups look separated. Seeing clusters can help us understand if the groups make sense. points with the same color are in the same cluster. This is a quick visual check for clustering quality. We use income and spending for easy viewing. Running the cell now. The scatter plot visualizes the clusters found by the algorithm, grouping customers based on their scaled annual income and spending score. Notice how points with the same color form distinct groups, showing how clustering separates similar data points. This helps us understand how customers are segmented for targeted marketing or analysis. Next, we will measure how good our clustering really is. How do we know if clusters are good? Visuals help, but we need metrics to really judge clusters. There are many ways: inertia, silhouette score, Davies-Bouldin, Calinski-Harabasz, and more. Running the cell now. Let us walk through some key metrics for clustering evaluation. Inertia measures how close each point is to its cluster center. Lower values mean tighter, better clusters. Running the cell now. The output shows the inertia value of 295.46, which measures the total square distance between samples and their nearest cluster center. Lower values indicate tighter, more cohesive clusters. In the context of this lesson, inertia helps quantify how well the k-means algorithm grouped the data, complementing visual inspection with a clear metric for cluster quality. Try comparing inertia with different numbers of clusters. Silhouette score shows how well points fit in their cluster. Scores closer to 1 are best. If the score is low, your clusters might overlap. This is popular for quick cluster quality checks. Running the cell now. The silhouette score of 0.36 indicates moderate clustering quality, meaning points are somewhat similar to their own clusters but there's notable overlap with others. This metric helps quantify what visuals suggest, giving us a clear numerical way to evaluate how well separated the clusters are. Higher scores closer to 1 would show stronger, more distinct clusters. Try clustering with more or fewer groups and see if the silhouette score improves. This line is a comment explaining the Davies-Bouldin index and its purpose. Here, we import the function to calculate the Davies-Bouldin index from sklearn. We compute the Davies-Bouldin score using the scaled data and cluster labels. Finally, we print the rounded Davies-Bouldin index to see how good the clustering is. Running the cell now. The Davies-Bouldin index here is 1.03, which quantifies how well separated and compact the clusters are. Lower values indicate better clustering with less overlap. This metric complements visuals by giving an objective measure to compare cluster quality, helping us decide if the chosen clustering truly captures distinct groups. Next, let us try another metric for clustering evaluation. This is a comment explaining the Calinski-Harabasz score metric. Import the Calinski-Harabasz scoring function from scikit-learn. Calculate the Calinski-Harabasz score using the scaled data and cluster labels. Print the Calinski-Harabasz score rounded down to the nearest integer. Running the cell now. Here we calculate the Calinski-Harabasz score, a metric where higher values indicate better defined clusters with clear separation. The score of 101 suggests a moderate clustering structure based on our scaled data and labels. This helps quantify cluster quality beyond visual inspection, supporting more objective evaluation. Now let us see how choosing number of clusters changes these scores. This comment explains we are trying different numbers of clusters and comparing their silhouette scores. Initialize an empty list to store silhouette scores for each k. Loop over k values from 2 to 6 inclusive to test cluster counts. Create a k-means model with k clusters and a fixed random state for reproducibility. Fit the k-means model to the scaled data and predict cluster labels. Calculate the silhouette score to measure how well the data is clustered. Round the silhouette score to 2 decimal places and add it to the scores list. Print all the silhouette scores corresponding to k values from 2 to 6. Running the cell now. Here, we see silhouette scores for cluster counts from 2 to 6, which measure how well separated the clusters are. The higher, the better. Notice the steady increase in the scores, suggesting that adding more clusters improves separation according to this metric. This helps us quantitatively evaluate different K values rather than relying solely on visual inspection. Practice: try changing the feature columns or playing with K values. Interpreting cluster results. Look for well-separated, compact clusters with good scores. Remember, metrics are just guides, real meaning comes from knowing the business or system. No metric can tell you if clusters truly matter for your goal. Running the cell now. What might these clusters mean for a mall marketing team? We can see the average age, income, and spending for each group. This helps us describe each cluster in simple words. Real-world teams use reports like this for decisions. Running the cell now. This output shows the average age, income, and spending score for each cluster, helping us compare their profiles. Notice Cluster 1 has the highest income and spending score, indicating likely high-value customers, while Cluster 0 is older with lower spending. These differences reflect how distinct and meaningful the clusters are, aligning with our goal to identify well-separated groups for targeted strategies. Try naming each cluster in your own words. Time for you to experiment. Let us try picking our own number of clusters. After running, compare the silhouette score to earlier results. This hands-on test helps learn which K works well. Test several values to see how the score changes. Running the cell now. The silhouette score of 0.4 suggests the clusters are moderately separated but not very distinct. This output helps you evaluate if your chosen number of clusters, K, yields compact, well-separated groups, guiding you before deeper business interpretation. Remember, a higher score generally indicates clearer cluster boundaries, but the final judgment depends on domain understanding. Which K gives the best score for this dataset? Let us know in the comments below. Common pitfalls. Letting outliers affect clusters too much. Using non-numeric data by accident. Assuming metrics always mean business value. Fix these with good prep, checks, and business sense. Running the cell now. Next, some final helpful tips before our wrap-up. The elbow method helps find the best number of clusters. Look for the point where inertia stops dropping quickly. This elbow is often your ideal K. Sometimes pictures help us decide better than just numbers. Try it with new data if you are unsure about cluster count. Running the cell now. This plot shows the elbow method used to find the optimal number of clusters by visualizing inertia values for K from 1 to 7. Notice how inertia decreases sharply at first but then levels off, indicating diminishing returns. This elbow point suggests the best K to avoid overfitting or underfitting. This helps prevent common pitfalls like selecting too many clusters influenced by outliers or irrelevant data. Practice: try the elbow method for a range bigger than 7. Challenge: try different sets of features, like just age and income. Run clustering, then interpret cluster results. Plot their silhouette scores, compare, and explain in a sentence. Share your results and favorite insights. Running the cell now. Pause the video and try these for hands-on progress. Recap. Cluster evaluation is about checking if groups are meaningful, not just splitting up data. Use multiple metrics like silhouette score and inertia. Always connect your results back to the real-world goal. With practice, this gets easier. Running the cell now. Remember, practice is key to learning data mining. Thanks for learning cluster evaluation. Try these techniques with your own datasets next. If this was helpful, like, subscribe, and see the channel for more hands-on lessons. See you in the next week. Running the cell now.